So, now let us look at the other end, t equal to 0. The math teacher's equation will say that at t equal to 0 you get Vc of 0 equals A. Plus V, whereas the circuits teacher will automatically tell you that it is V0. That is the difference between the two. Now, clearly the circuits teacher knows something that the mathematics teacher does not. Let us see what it is. In order to understand where we are going, let me look at the math equation for the solution, which is that it is A e to the power minus t by RC plus V. Let us plot this graph for various choices of A. I will make a nice big graph so that everybody can see it very easily. This is time and this is Vc, right. Now, the equation we want to plot is Vc of t equals A e to the minus t by RC plus, right. This is what we want to plot. All right. Now, A is an arbitrary constant. So, I can choose different values of A and get different curves on this graph. Let me start with choosing A equal to 0. If I choose A equal to 0, the entire first term disappears, and if for example I choose V to be equal to this much, let us say that this is the value of the battery voltage, then the first curve I get, which corresponds to the case when A equal to 0, is this, a straight line. So, I will put an arrow over here and say that this corresponds to A equal to 0. This corresponds to A equal to 0. Next, let me choose A to be some other number. A plus V is the answer we will get. So, suppose I choose A equal to 1, then I should get V plus 1 as the value of Vc at t equal to 0, and subsequently as t goes to infinity, the capacitor voltage must end up at V. So, it essentially takes an exponential trajectory starting from A plus V and ending at V. Let us say if A is equal to say this, then approximately here you will have A plus V, and from here you would get a curve like this. This for one value of A. Now, let us make another larger value of A. If A is larger, then A plus V would be somewhere over here and you would get a curve like this. Still larger value of A, you would get a curve like this. And there is absolutely nothing to stop A from becoming negative. So, I could choose A equal to minus V, for example, choose A equal to minus V, and A plus V will just be equal to 0. The initial condition, the initial value of capacitor voltage would be A plus V equals 0. The final value would of course remain equal to V, and you would get a curve like this. More values, negative values, another negative value. So, you get this bundle of curves for various values of A. So, the mathematician says, I need some more information to give a single unique solution as a function of time, and that information is not captured by the equation itself. Remember that I said that while the differential equation certainly summarizes certain aspects of the behavior of the physical system, it is however not an exhaustive description of the physical system. We are now coming to the point of finding out what is the part that the differential equation misses, and that is exactly what we are coming to over here. What the differential equation tells you is the rate at which it tends, the rate at which the voltage on the capacitor changes with time. That is completely captured by the root of the characteristic equation, namely 1 by RC. That tells you that part. Also, the differential equation is capable of telling you what is the final value of the capacitor voltage. We know that that is going to be V. However, you can have a lot of curves, such as the curves that we have drawn over here on this board, all of which satisfy both these properties. They are all exponentials with time constants of 1 by RC. They are all exponentials which end or tend towards V, but they still differ from each other. They are not all the same curve. So, we have to see how they differ from each other. Clearly, one very important point you can observe with this set of curves is that no two curves in this set intersect, though of course the way I have drawn it, they may appear to be intersecting in some places. No two curves in this bundle ever intersect. Let me even actually write this down. This is a very important observation, though it is only valid for a set of solutions for a first order differential equation. That is, that no two curves of the complete solution ever intersect. So, what do I have to do if I have to pick a particular curve out of this bundle? What do I have to do to pick a particular curve? Very simple. In order to pick a particular curve out of this bundle, I have to do two things. A, choose any instant of time say t equal to t naught. Let me put this on this graph somewhere over here. Let us say that this is t naught, and then at that instant of time let me just draw a vertical line. If I look at all these curves in the bundle, and remember that there is an infinite number of curves in this bundle, though we have drawn just a few examples of the different curves that can be there, at every point on the surface of this sheet you can put your finger on any point here and there will be a curve going through that point like this. Sorry, I can choose any point like this and there will be a curve going through that point. That curve will also be a solution to this equation. So, there is an infinite number of curves here and they literally cover the entire plane of this graph. There are no places where there are no curves. But if you put your pen down at a particular point on the surface, then at that point, through that point, there will be only one curve passing, one unique curve passing through any point on the surface. This is an important thing, and therefore, what I have said here can continue now. Step A was to choose any instant. Step B is to specify the capacitor voltage at that instant. The moment I specify a certain value of capacitor voltage, I will uniquely pick a particular curve. So, for example, on this vertical line, which represents different voltage values on this vertical line over here, I can choose, say, this as the capacitor voltage, this. If I choose this, then I immediately get this curve which I have already drawn. That gets fixed for all time. So, I only chose a particular instant of time and specified the capacitor voltage at that instant of time, and I have immediately been able to isolate a particular curve for all time. That is important and that is interesting. Now, if I wanted to pick that same curve, but instead of t0 I was working at some other instant t1, let us say this is t1, then I would draw a vertical line here, and in order to pick the same curve that I did before, I will now need to specify a different capacitor voltage, namely this. I will choose this capacitor voltage now. So, this means that depending upon which instant you want to specify the capacitor voltage, you are probably going to have to specify a different capacitor voltage. This is, however, not true for all curves. Remember the curve we got for A equal to 0, the perfect horizontal line. That is a unique, a very special kind of solution out of this family of solutions, because irrespective of what instant of time you choose, you just have to specify that Vc equals V and you will get that particular curve, that particular straight line curve in this case. So, you will probably have to specify a different capacitor voltage for different instants of time in order to pick a curve of your choice, but not necessarily. Okay. Now, let us move on. We have learnt a few things. We have said that we have to choose a particular capacitor voltage. What the electrical engineer calls that is, he calls that the specification of an initial condition. However, the shortcoming of the stunted way of learning how to solve these things from a purely circuit theoretic point of view is that when the textbook says initial condition, it normally refers to an instant when something important has happened in the circuit, like some switch was opened or some switch was closed. It is only at that instant of time that the capacitor voltage is supposed to be the initial condition. That means there is an impression conveyed that there is something special about that instant of time that represents the initial instant of time, and all other subsequent instants cannot be called initial instants. That is why this terminology of speaking of initial conditions is slightly problematic, and that is also why I have not used the word initial condition, I have used the word auxiliary condition. When I say auxiliary condition, I am not confining myself to refer to or to address some particular initial state, some special state when something interesting happened, like a switch was closed or like a switch was opened. I do not have to confine myself to any such some special kinds of points of time. It could be any point of time, and we could easily appreciate that by going back to these graphs. You have all these graphs over here, right? Now, we said that for the circuit, which I think is available at an earlier panel, still earlier. Well, okay, let me just redraw the circuit over here. We said that we had a capacitor, a resistor, a switch which was closed at t equal to 0, this was C, this was R, and then we had this battery over here which had a voltage V, and we were told that Vc of 0 equals V0. This is the circuit we had over with us earlier. Now, at t equal to 0, we know that the capacitor voltage is V0, and knowing that, we have gone ahead and found the electrical engineer's solution to the problem, which was given by this equation, by this particular equation over here. We have this solution. Since we knew that the switch was closed at that time, we used that and we found the solution. But the point I want to make is there is nothing special about any initial instant. Any instant at all can be treated as the initial instant. For example, I can choose the t1 shown in this graph as the initial instant. Then what will be the capacitor voltage be? It will be some number which we will call, say, Vc of t1. So, let the capacitor voltage be specified at t equal to t1 instead of t equal to 0. Let V1 be equal to Vc at t1. Suppose V1 is what we use to denote Vc at t1. Then can we now write the differential equation knowing fully well, or can we solve the differential equation knowing fully well that the circuit switch was not closed at t1 but it was closed earlier? Is this going to be a problem for us? Though the switch was closed at some earlier instant of time, we want to solve the equation completely, get the unique physical solution with a knowledge not of the capacitor voltage at t equal to 0, but of the capacitor's voltage at t equal to t1. Now, if your knowledge is incomplete, if your understanding of the theory of differential equations and its application to circuits is incomplete, you will say, well, I really do not know how to use the capacitor voltage at t1 to get a unique solution, though of course I know how to use it, how to use the capacitor voltage at t equal to 0 to get a unique solution. Now, there is no problem. Suppose we want to solve Vc of t for t greater than t1. All you have to do is to get the same curve, but the latter part of that curve. In short, instead of finding this entire curve, we want to find only, if I could change colors, I will just, instead of getting the entire curve, I just want to get this part of the curve. थोड़ा पीछे कर दीजिए चाहिए तो. You just want to get this part of the same curve as the solution. I have just drawn it beside it. You can see the red curve now. That is what I want to get as the solution. So, how do you go about it? Now, the initial condition does not correspond to any important event in the life of the capacitor or in the life of the circuit when some switch was closed or opened. It just refers to an arbitrary point of time in its continuous evolution, except that we know the capacitor voltage at that time, and we know that we have given it a name, we have called it V1. So, we will simply call it, we will now write the equation for the solution. We will write that Vc of t for t greater than or equal to t1 is equal to V1 minus V e to the minus t by RC plus V. All I did was to replace V0 by V1, and now I have the curve that describes the solution to the equation subsequent to t equal to t1. You can verify this. This equation should evaluate to V1 when you put t equal to t1. Does it? If you put t equal to t1, it will not. We have missed something over here, and that is that here, since the equation has got shifted, what we should really write over here is this. Instead of writing e to the power minus t by RC, what we should really write is e to the power minus t minus t1 by RC plus V. Now, we have made the correction that was required. The intuitive thing was not right. Now, let us see what we get. Put t equal to t1 over here. The exponent goes to 0 and you get V1 minus V plus V equals V1. So, Vc at t1 comes out to be equal to V1, and of course, the limit as Vc goes to infinity, the limit as t goes to infinity of Vc of t is still equal to V. There is no change in that. Fine. So, now we have demolished the seeming sacredness of choosing the initial instant or the initial condition to happen only when an event of some importance has occurred in the circuit, such as a switch opening or closing. We can choose any instant of time as the initial instant. It does not have to be only the instant at which something happened. So, that is one important step forward. This important step was possible because if we go back to the curves, we note that no two curves in this bundle happen to be intersecting. Since no two curves are intersecting, as I said earlier, in order to pick a particular curve out of this set of curves, one does not have to confine oneself to t equal to 0. One can confine oneself to any instant of time on the positive time axis, and at that instant of time specify the capacitor voltage. The moment you specify the capacitor voltage, that becomes the so called initial condition. But more generally, since the terminology is not confined to anything initial, the curve has existed from t equal to 0, but you are specifying a value at t equal to t1 greater than 0. We just call this the auxiliary condition. So, this is a generalization of the approach that is often used in solving simple circuits. You can specify a capacitor voltage or a certain condition in the circuit at any instant of time. Well, that is as far as first order differential equations are concerned. Now, if you want to go to higher order differential equations, let us just take a brief glance at what happens with a second order differential equation. Here there are two arbitrary constants, because you will have a sum of two exponentials in the general case, provided the roots are not repeated. So, you will have a e to the power s1 t plus b e to the power s2 t as the solution to the homogeneous equation, plus you will have what you call psi of t, which is the solution to the non-homogeneous equation. This now, since there are two arbitrary constants, if you now try to plot all the possible solutions, the curve of all possible solutions, then what you get here is a much bigger mess. You will get, briefly speaking, I am not even going to try to plot it because the previous graph was messy enough. What you will get is, unlike the previous case, unlike the first order case, let me write down the difference. Unlike the case of the first order equation, where only one curve passed through a point on the plane of the graph, of the graph of y of t versus t. Here an infinite number of curves will pass through the point. Pass through each point. And yet there will be something available to distinguish these different curves. The different solution curves that all pass through the same point on the graph will differ in slope. In short, no two different solutions, no two distinct solutions will both pass through the same point, B have the same slope at that point. So, in the first order case, we were able to pick a particular solution out of the bundle of infinite number of solutions by specifying a point of time of our choice and specifying the value of the curve at that point, at that instant of time. That is, we just had to pick the point on the graph surface. Now, we have to pick the point on the graph surface, that is, having chosen an instant of time, we have to tell the value, we have to specify the value. Second, we also have to specify the slope. Thus, the difference is the following. Now, in order to pinpoint a particular curve, of our choice, we first choose a time instant as before, that means as in the first order case. B, specify the value of the curve at that instant of time. At that instant, and C, specify the slope If we do all these three things, then we would be pinpointing a unique, a specific solution out of the infinite number of solutions. Here, in some sense, the number of solutions is doubly infinite, because there are two arbitrary constants, each of which can take one out of an infinite set of possible values, and it gets triply infinite for a third order equation, quadruply infinite for a fourth order equation, and so on and so forth. It gets more and more complicated. So, for example, for a third order equation, I am not even going to write it down. The way you would pick a specific solution out of the bundle of triply infinite different solutions is go through step A, choose a time instant as before. Step B, specify the value. Step C, specify the slope. Step D, specify the second derivative, the value of the second derivative. So, in short, for an nth order differential equation, to pinpoint a particular solution, a specific solution out of the n-tuply infinite possible solutions that the mathematical solution throws up, you will choose any instant of time of your choice. This is important for whether you are solving a first order equation or an nth order equation. You are always free to choose the instant of your liking. You do not have to choose anything like an initial instant, and that is why we just call it the auxiliary point of time at which we are specifying the curve. Now, choose the instant and then go through B, C, D, so on and so forth, where you specify the value, specify the first derivative, specify the second derivative, specify the nth derivative. If you have done all these, then you have chosen a particular curve. So that's how the importance of these so-called auxiliary conditions is brought to our understanding. Earlier, all we have known is that initial conditions have to be specified at t equal to 0. There is nothing special about t equal to 0, as I am saying over and over again. You can choose any t you like and specify a sufficient number of characteristics of the solution depending upon the order of the differential equation. Instead of choosing just one particular instant of time and specifying the value, the derivative, the second derivative and so on, as I just mentioned for the nth order equation, there are several other options available, and it is important to understand this as well. For example, in the case of a second order equation, since we have a double infinity of possible solutions, we could take two different instants of time, say t1 and t2, and specify the value at t1 as well as the value at t2. Even this is sufficient to isolate a particular solution, a unique solution out of all the solutions that are there. Even this is possible. So many options are there, and they are all equivalent to each other. They help us specify the conditions of the physical system which is being represented by the differential equation. So let's summarize what we have learnt today before we close. On the relationship between differential equations that describe systems and the systems themselves. One, the description provided by the differential equation alone is incomplete though not incorrect. Two, additional information needs to be supplied Three, the additional information can be supplied in a variety of forms at instants of time of our choosing. Four, if this additional information is adequate, and this depends on the order of the system, then a unique solution will emerge that matches the behavior of the system, the behavior of the physical system. This only addresses the issue of multiplicity of solutions. What we are going to take up in the next part of this course is how other issues, like for example the linearity of a system or notions like the time invariance of a system, all these things that we are conventionally accustomed to use, all these terms that we are conventionally accustomed to use to describe physical systems, how they relate to the nature of the differential equation itself.